Alright, 1008, construct binary search tree from preorder traversal. Return the root node of a binary search tree that matches the given preorder traversal. Recall that a binary search tree is a binary tree where every node, any descendant of the node left, the node does. Okay, I know what a binary search tree is. Okay. So the input is because they okay. Sorry, I was reading the input format and stuff like this, so I get a little confused. Thanks for the follow. Okay, Marky. But yeah, because the input and output looks the same, but this is actually a list where the output is a tree, and we have to return the entire tree. Okay. Preorder. Which one is preorder again? That's the one that does the node first. So basically, I mean, I think that's yeah. I mean, I think since this is a binary search tree, we just have to kind of go one by one. So that's kind of yeah. So we just construct this there are a couple of ways to do it. I'm going to do it with that first search, and you just kind of keep track of the current node. Yeah, okay. And then now, so you always want to construct a new node with the the font of the pre-order list, because that means that's the node that you're seeing. So let's do that. I'm just thinking right now about how to kind of how to kick off the base case. But I mean, like I think I did a similar problem on stream where, given the pre-order and the post-order, well, pre-order and in-order, how to solve it. So it's not that different from that one. The difference is that this is a binary search tree, so from that you could kind of deduce it. Because if you look at the input, just to be clear, if you look at 8, that means that all the numbers that are smaller than 8 will be on the left side, and all the numbers that are bigger than 8 will be on the right side, right? So then you could kind of break down the tree that way and then construct it that way. And the way that you can do this is n square because of that reason, but you can actually do better by binary searching, so it becomes n log n. Maybe you could even do it in, if you do it smaller, you could do an O of n as well. And yeah, maybe that's the way I'll do it. I'll try to do it. Okay. First of all, yeah, let's just create a new root node. As you go to new tree node with preorder dot. Let's put this in a queue so I could. So as you go to collections dot deck of preorder. So then we could just pop the left and all one time, and then now we just recurse. I mean, you could do a. I'm just thinking a little bit. I mean, the way I would do about it is using a stack. But I'm just thinking about whether to do an implicit stack or explicit stack. So yeah, I think I'm just going to do it with an explicit stack. So then, let's just say push, no, pen. And then, well, length of stack is greater than 0. I want to do it this way. Actually, I kind of want to do it recursively. Sorry, friends. And then now you're just giving the current root. current node, and then if yeah, okay. So now as you go to traversal dot pop left, which is the current which is the current value, and then if current value is less than no dot value, is it dot val? Okay, then you go left, right? No dot left. I guess I shouldn't pop left yet. Then let's just call it peak. What's a peak? I guess just this, right? Also have check bounds. Otherwise, I guess we just return in this case. So here is a node dot left is you go to tree node of current value, and then you just go left. That was something like that. I think should be okay, maybe. But now I have to do. I'm screwing it up a little bit. Hang on, because I think I have to. Because this could happen twice. So you want to do all this stuff, and then I have to pop though. Okay. And then try again. Maybe I could use some Python shenanigans to make this cleaner, but oops. Yeah, maybe that's okay enough. Let's take a look. Oh, I have to. A little bit copy and paste. I would maybe, but I don't even know what this looks like. It's very hard to visualize actually. But it seems like what I'm doing is I'm drawing the 10 to the right of the 7, which clearly should not be. Oh. I would say during competitive programming, given that n is 100, that I would probably just do the n square way. But there's definitely a linear way, which is why I'm thinking a little bit. And all values are distinct, so I don't have to worry about that. But I think I just have to keep track of the bounds a little bit. Because because we want to check this if only also and wow is On that subtree. No, I don't. This is a weird way of doing it actually, because you have to kind of recursively think about it. I guess in the other case, I just do the n square algorithm. Is there no... So there's definitely well, there's definitely an n square algorithm, but is there even an n log n? Well, is it n square? No, I guess it's, well, it degenerates to n square. It has the same actual performance profile of quicksort, because you could look at, it's just the same thing as doing quicksort except for using the first index as a pivot, and then just looking for an entire time linearly, which has a same degenerate case as quicksort as a result. Maybe there isn't. I think I'm just also trying to think about everything here has to be. Because you have to think about I think about this second. Because I think what I wanted to do is prevent everything, like in this case, on the example case, everything that's on the left of 8 would not be. So I think now I just have to keep track on the root that, no, is it on the root? On each node, how would I know on each node not to keep going? And then also do that for each of the sub cases, right? Maybe that's okay, actually. I gotta stop calling everything DFS, but that's besides the point. Okay, I think I don't like the way I'm doing this here. So what I want to do is, this is okay. And I think I want to do something. Actually, I think this is okay. Yeah, maybe I just do it like this, where this is the right side of it, and then for each one, okay, maybe I want to do something like this, and then now I can separate them differently, and then now the bound is just, I don't know, the last one. Oh no, there's, you got a tree node of, well, we should check that first, actually. If none, if is bigger than right, also return none. Otherwise we do this thingy. And then now, when we return node dot left is equal to, I was trying to get it in one DFS, and I think that's where I was a little bit confused as a result. Wait, where am I DFSing from root? No, I don't need the root. I can way past it. So I don't need this. And then the bound is node dot left dot right. No, node dot right currently. And then node dot right is equal to the DFS of the right. Okay. Because yeah, your left has, all your numbers on the left has to be smaller than the current number. All the things on the right. Did I misspell something? 925. Oh, whoops. I removed the node because I wasn't using it. And then everything on the right has to be a bit smaller than the right that's currently. Okay. I got a little mixed up, but okay, cool. I think that's okay. Oh no. Well, yeah, I guess I should have known that one. What's gonna happen? That's just me being careless. I guess I could just do infinity. I mean, that was just a crappy shortcut. This is just my way of doing infinity real quickly. Don't know if I recommend on an interview, but I mean, that'll still be the upper bound, but I just don't want to add in more edge cases for it. Cool. How long did I spend on this one? About 15 minutes, but I did talk a bit about it. But yeah, cool. Yeah, again, this is another tree problem, which means I generally always recommend practicing tree problems just because that's what the market is asking these days. And definitely pre-order, in order, post-order. These are things that everyone talks about because it's just part of the fundamental things that everyone should know, give it, for better or for worse. So definitely recommend that. Yeah, in this case, there are a couple of ways to do it. As I said, there's the pivot one, but you could just take off digits one at a time, and then in a weird way, there's also the left. If you think about bounding your depth first search, your left is actually technically your smallest value. But so then in theory, if you want to have a better visualization, this is a depth first search from 0. I don't know the negative values. I guess technically they could be negative values, but negative infinity to value that row, and then value that row to infinity. So kind of just putting the universe for that to be fitting there. And I kind of keep track of it. And there's an implicit left that is negative infinity, and also the previous value that gets popped off the traversal because you know that there's no more smaller values that could show up by the time it's your turn. That's why that's one of the implicit parameters. So that does make things a little bit more confusing, but yeah. But yeah, so definitely recommend practicing this. This is O of n because we look at each node once. We use O of n space, but that's because that's output sensitive in the sense that you cannot do better than O of n space because you need to return the tree that you construct from scratch, which is O of n, right? Extra space, you could probably be a little bit cheaper. I mean, I converted to a deck, but it's the same space that the pre-order is in. It's just in a different format. But yeah. Yeah, you could. I mean, I think the way that I thought about it, but maybe I could have been a little bit clearer about it, is just clearing out the left and the right. So that this is actually very similar to the previous problem, except for in the previous problem we're like, well, now you assume everything is inside, and then like if you write it this way, then you also write this is bigger than left, is smaller than left, we return none, but again, this cannot happen because if it does happen, a previous processing would have consumed it, right? So that's why there's a implicit left. And again, this would be like negative infinity to root that value, and then root that value to infinity. And then again, this is just the left to that, the value to that, right? So that's maybe a clear way to splitting up the space. And then when you do it this way, you notice that because of this condition where if you look at the depth first search, which is an implicit stack, when it comes to look at the preorder, well, by the time you get to the right side of things, all the number that's smaller than the like in this case, all the numbers that are smaller than, well, like negative infinity doesn't matter, right? Obviously, just every number. But by the time you get to the root dot right, every number that's smaller than root dot value would have already been consumed by root dot left. And similarly, no dot left. Well, everything that's smaller than left that we put in, that was already consumed by something else. So you won't never have to worry about it. And because if you kind of break them up into spaces, like a partition of the number space, but yeah, and then no dot right, like obviously all the numbers that before no dot left, literally the previous line would have done it. So yeah, so that's kind of how I would do it, and everything's O of n, and that's the invariant, as Mbrax points out. Yeah, cool. I mean, a fun problem. Definitely took me, and well, that's just a silly mistake. I was trying to get away without writing infinity, but there is that one case where there's only one root node, which I should have known about. So maybe these are things to think about. But that's when you try to get too cute, is when some of these happens. But yeah, O of n, and definitely will come into play. So I definitely recommend studying this. Yeah, cool. Cool.